Can't wait.
Okay, I'll do. Right, so this talk is going to, my name is Labelle, and I work as a internal vulnerability researcher at Broadcom, testing their various mainframe products. So I used to be a external consultant, just going around, mucking around with other people's mainframes. But yeah, this talk is going to be about how mainframes work at like quite a low level, and then how to use that to exploit some programs. So the best thing that when you end up testing mainframe products is that this talk specifically is going to be about COS. There's some other mainframes out there, but they're even weirder. And the COS is running in basically every bank, every insurance place, every airline. So it's doing pretty critical stuff. And it's also got typically each system will have like thousands of local users. So a local privilege exploit on a mainframe basically gives you full access to the entire bank's like critical stuff. So if you find one there, it's pretty good. The ZOS is running on its own different architecture. So instead of x86 or ARM, it's running on ZArch. And this is a very CISC architecture. And so, for example, this is something that tripped me up one time. I was reverse engineering a C program, and this C program used a string copy. But string copy, when it
Hey Jake.
when it compiled, oh yeah, sorry.
Sorry to interrupt. Is it possible you could get into presentation mode? We can see your slides, but they're very, very small.
Oh, okay, how do I do that?
Should be like a tab presentation.
Slideshow?
Oh, it's
Use
under
slideshow.
leave. Oh, it's in leave.
Yeah.
If I just do this one?
That's what it's.
Is that not what I was, or?
Hasn't updated on our side yet.
LibreOffice.
Here.
So like a.
Can you try, according to ChatGPT, can you try F5 or Shift F5? Okay, just trust me, bro. It'll be fine.
I just pressed it. Is it still just showing in the window? Oh, okay. I'm going to try just sharing my screen instead then. Maybe it's doing something weird with. Okay, sorry. My screen. Okay, does it?
Oh, that's money.
There you go.
That's it.
Okay, cool. Right. Ignore any random Discord messages that appear at the top of my screen then while I'm presenting. Okay, so when you see the C function move copy, the string copy, that compiles down to a single Z architecture assembly instruction, MVST move string instruction, and so. And this is just a picture, you probably can't see what it says, but this is the Z Architecture Principles of Operation, the POP book, which has, it's all of the different instructions and all the different things they can do, and it's 1,150 pages, so a little light reading. And the thing that most defines ZOS is that everything is a job. So for example, when you log in to a mainframe, what you're actually doing is submitting a job, and that starts your user running. And so this below here is what used to be something that you would put into a punch card and submit to the internal reader, which is this is a JCL, and you submit this, and then after the job runs in a asynchronous way, you would go get the output from the spool, and you could read out and see what your job did. And some of the people I work with have been working on mainframes for the last 40 years, and how it used to work is whenever there was a bug in a program or a product, you would get all of the spool coming out of the printer, you would package it up, so a bank would package that up in a box, and then FedEx to the people to fix it. So that would be the dump reading of previous times. And the other thing that's important is that each job runs in its own address space. So this is how, if you run this job and someone else has their login job, they're not able to interact and change each other's memory. And so the way this works is that each address on Linux or Windows, everything is like having the private memory, where you can only edit memory in your address space. All the memory in your address space you can edit, and it's just something you could write to. Whereas in ZOS, it's different. There's a concept of private and shared memory. And so private memory is the memory your program can muck around with and change. And then there's shared memory, and this is kind of like the kernel address space, but inside of it's addressable inside of every single address space. So everyone is able to look at everyone can address what would be the kernel code on the mainframe. And you might be thinking, how is this safe? How could you do this without basically making it always vulnerable to everything? And the way that mainframes work is that every single page of memory has a storage key. And this is so every page will have a storage key, and then your program will also have what's called a PSW, and you can think of this like a really large register containing your next instruction address, your condition codes, stuff like that. And it will also contain a key. And what this means is that if you're in key 8 and you want to write to memory, that memory has to be in key 8, or else it won't allow you to write there. And so there's certain addresses which are also fetch protected. So not only do you need to be in it to write to that address, but you also need to be, to read anything from that address, you also need to be in that key. There's a special key, which is key 0. And if your program is in key 0, you're allowed to read to write to anything you want. And so the exploit, the way every exploit works on a mainframe is your objective is to get into key 0 through some sort of code execution way. And then from there, you can edit anything on the system and take over what you want. So that's the target. So how does a program get into key 0? And there's a couple of ways you can do it, but probably the way that's most easiest to explain is APF authorization. And so you can think of so this is this data set called tcp/ip.cesar.tcp is a authorized library on the system. And you can kind of think of an authorized library like a folder, which if a program is called from this folder, and also it's linked with a code AC1, which you can see on in the picture, it is then has one of the bits set in the private memory, but a private memory for that you're not allowed to overwrite. That allows you to run this bit is called the JSCB auth bit. So if in your program this bit is set to 1, it allows you to run a special command called mode set. And what mode set does is it allows you to edit which key you're in. And so when we're testing mainframe code, what we really want to test is programs that are in authorized libraries and also linked AC1, because then if we get code execution, we can run the mode set command and then we can take over, do whatever we want. So one of the problems with the programs that you link AC1 should be programs that you call as the job step program. And so if you see in this JCL I provided, the job step program is the MVP main, so exec pgm equals MVP main, which means that the MVP main is the job step program. And then from there, if you call any other program, you don't lose the JSCB auth bit. That still stays as 1. However, in the step lib, any program, if any program in the step lib is not APF authorized, then the JSCB auth bit will not be set. And so this program, MVP main, what I'll show you is that it will call any program that you set in the POM. And so on a Linux system, if you had a program that called any other program that was a set UID root program, this would be an incredibly easy exploit. You could literally just put that program there. It would get called. You'd get root, and then it would be game over. But it's a little bit more different on mainframes. So at the moment, we tried to call this program. I put mode test, and it tries to grab it from the step lib, and because that program doesn't exist, it will just give us an error. So let's compile a program and then put it in a non-APF authorized library to show that the JSCB auth bit would get unflipped. So this is just a program that will set out a WTO that just sends a message to the spool. Then it will run this SVC 107, which is the mode set command. And if we do this second WTO, that means we know that we've done the mode set command. And so from there, we could have done anything. So we compile this program, we put it in a library, and we put it in this, my own data set. So jake.nor.loadlib. And so because we're running as a low privileged user, we don't have the ability to compile, to turn a data set APF authorized. What's going to happen is when we call this program, it will tell us that the program is not executing with an authorization code of AC1, and so it will just error out. And so what the attacker needs to do to be able to exploit this program is they need to find a module that already exists in an APF authorized data set. And so, for example, a data set that will be on every single system is the sys1.linklib. This is the default IBM library that will be on every single mainframe system. So if you find I call them APF gadgets, so basically a program that you can call, that you can use to get control after it gets called. So in this case, the one that we will use is the ant usu BT program. And the reason why we use this program is so first it'll be on every single system, and also it handles register 1 in such a way that when it receives input, it will give you back code execution on something a little bit after the address given to it in register 1. So in this case, I used a different, so in this case we use the gadget IAS GNRMT. This is another module in sys1.linklib. And this ESA main, MVP main program, it has an alias of ESA main, so it's the same program. The way it works is you give it a program, then you give it a comma, and then it calls that program with this stuff in register 1 to that program that you're calling. So as you can see in the step lib, I have the DSN equals sys1.linklib, so it will grab this IES, GA, and RMT from sys1.linklib. It will call that program, and it will call that program with CCC, DDD, etc. in register 1. And this is this ESA main, MVP main, was a program that was on TOS mainframes for at least 20 odd years that was doing this, and just people didn't realize that this was a vulnerable pattern that would basically just make that you could exploit any system. But yeah, so then the way that this IES, GAN, RMT module works is that, I can't remember how many bytes that is after the register 1, it will grab this 00009600 address from the register 1, and then it will branch to it. And the other thing about Z architecture is that it's big endian. Doesn't really make that big of a difference, just something to be aware of. Okay, and then at this address 00009600, we put the code in that we want to run. So in this case, I put 07000700, which is 2 NOP addresses, just so I make certain I'm in the right place. Then a 4110003C, which is the load address, R1. Put 3C into R1, and then run the mode set instruction, OA6B. And so once this program runs, what will happen is that it will branch to this part, which will be stored in 00096 in R1, and then it will then execute this code, and you will see that the key of the program will be in key 0 and supervisor state, and from there you can do basically anything on the system. So as you can see, it's branched to this 9600 address, and this PSW at time of error shows that this 0 means it was in key 0, and this C means that it was in supervisor state. I kind of ran through that, but I have no clue what the time was. But yeah, so that was a IBM program that was on every single system, and then the gadget was an IBM program. And so using those 2 modules, you could gain local code execution in an APF authorized state on any system. And as I was saying, every system, every mainframe has at least 1,000 human users who log on to it. And so if any one of those users is able to gain that access, they'll have full access to the system, because mainframes also have a very binary authorization state. You're either running as a problem state program that can do nothing, or you're running APF authorized and you're in key 0 and you have access to everything on the system. But yeah, is there any questions?
Thank you. Awesome. Let's see. You actually came in perfectly on time. Does anyone have any questions for Jake here?
In the room, or?
IBM ZOS LP is kind of sick, actually. I thought that was extremely cool. Hey, actually, I have a quick question for you, Jake. Is your research outside of this presentation here, is there like a blog post or other like research paper or other written publication documenting kind of your process and the research that you showcased in this presentation?
I'd probably say the best one is me and someone called Phil Young made a CTF using the 1980s. There's IBM and the government worked on a mainframe in the 1970s, the software, and so that was all had to be somewhat public source, and so anyone can run a 1970s mainframe on their own system. And so me and Phil Young made a DEF CON CTF challenge. I can't remember the exact link, but if you type in DEF CON CTF mainframe, you'll probably find it. It's on GitHub.
Awesome, very cool. Well, thank you very much again. Awesome talk, and hopefully the other speakers, or sorry, the other organizers have already talked to you, but we do have swag bags to send you, and apologies that the winter weather, we couldn't have you here. But thank you very much.
No problem. All right, thanks for the organizing, and yeah.
All right, thank you.